So the goal is for, I put the link to this slide deck in the Slack chat. So the goal is for everyone to split up. You'll talk about whatever problem you chose in Slack, and then sort of write up a report about what your main takeaways were from the discussion. And the goal is that we'll have these slides that we can all refer back to if we want to know sort of like, what is the state of the art in terms of this question? What are the open problems? What are, observations or modeling that people would really like to see done? So we have a little bit more of a roadmap for how to kind of make progress on some of these issues that people have raised. So, I mean, this is certainly not a comprehensive list of things you could discuss in your discussion section, but some ideas that we just started throwing out. What is the state of the art of the modeling? What is the best we can do right now? What observational constraints do we actually have on the problem? Is this problem unique to particular mass domains? This might be a sore point for me because I do a lot of low mass stellar evolution. And I think we have a little bit of an imbalance where there's a lot of people doing modeling in high mass. There's a lot more stars to observe in terms of low mass. So, can we help each other out with some of that? We haven't talked too much about this yet, but we have a lot of interesting new observational missions coming up. So are any of those particularly promising for addressing these problems? And of course, what new modeling approaches are needed? Do we need hydro? Do we need, adjustments to the 1D codes? So every group will ask for a representative from the group to come present, 5 minutes on this question and the main points we should take away from this conference about each of these.
So you should be able to pick an emoji that's in Slack that represents the topic that you'd like to join. And the idea is then they're in the slide deck on each. There's a question, you and your group will work to fill that out. Do you want to go through?
Yeah, so we can just quickly go through what we picked as questions. So the first one was what happens to eccentricity during mass transfer? So this one's come up a lot. I think this is a hot topic. We know that a lot of stuff is coming out of mass transfer eccentric. Possibly it's actually entering mass transfer eccentric, but we're usually modeling these things as circular. So what are the implications there, and where should we be going with that?
And then how do we actually measure the accretion efficiency during mass transfer? What is the efficiency? What happens if we get non-conservative mass transfer? What happens to the mass that's lost? That's come up quite a bit in these discussions.
Yeah, and then sort of related, a lot of people have been raising this issue of rotation in stars. And in a lot of cases, we very quickly spin up to critical rotation, and that limits the amount you can accrete. So, what are the theoretical expectations there in terms of when we're reaching this critical rotation rate? And we expect that that's limiting accretion. And then, the flip side of that is we know that there are systems where very conservative mass transfer is happening. So are our models really saying that's only happening in very close systems or in very particular situations that it can happen? And if not, do we have a problem here? Do we need new mechanisms to actually shed angular momentum in a lot of these cases? So there's a lot to dig into there, I think.
Yeah, and then in our discussions that we've been having about the stability of mass transfer, if case B, C, D mass transfer onto a main sequence star is actually more stable, which seems to be the consensus in some cases than we previously assumed. Should we be observing more of them? Where, how do we find them? And if we can't find them, why not? I mean, part of this question was, what are the systems what are the observational systems that are lurking out there that we don't see? How can we find them? How can we use new missions to actually answer some of these questions, and modeling as well? Like, what do the models predict? We already had from Jan's talk about some of these cases.
Yeah, number 5, I think some people are putting up their models and there's a quick slide, like what physics did we include in our models? So I would love if we could just kind of have a summary of like what things should be included in mass transfer models, like what stuff should we not be ignoring, and what are things that people haven't really looked into that might actually have a big impact on mass transfer.
Yeah, I mean, some of these things are uncertain for single stars, but I mean, then we double it with binaries. It's you know, it's an important thing. And then finally, you know, it came up yesterday about, you know, pre-main sequence star evolution. There are a lot of actually different fields that have very similar problems. You know, accretion is a universal process. What can we learn from other fields? Like, should we be talking to other communities where they've maybe made more advances? Should we be looking at what they've done? People like who do accretion onto X-ray binaries all the way to AGN, you know, should we be trying to make connections with other fields and other evolutionary phases across mass regimes? Those are the choices. And then we'll divide up. So I guess in Slack, if you could select, I don't know how are we, I should check, I can check on my.
Why don't you check how we're doing?
Okay, so has everybody,
well.
everybody divided themselves up? I think we'll have the, should we do dragons over there, unicorns over here, octopuses, and then on one of each of those tables, octopuses, bees, and ladybugs. Doesn't seem like anyone is doing the elephants, the whole like evolution, but maybe we don't have those communities here, so it's a bit of a
So we will get back together. What
oh
time?
yeah.
What time do we want to get back together?
I would say maybe you should reiterate where it is or write on the board, like dragon here.
Yeah.
Sure. So we want to.
We have until 12, half an hour to come back.
Yeah, so we have 5 topics, so 5 minutes each. So let's all make sure we're back in the room by 11:30, so we can report back.
Cool. Okay, so dragons over there. Oh, what?
You want me to write?
Yeah, write it on the board.
Dragons.
Or draw a team of dragon.
If you're more artistic, you can draw. Yeah. Unicorns over here. Unicorns over here.
Nice.
And then octopus. We'll go octopus. Oh my God. These ladybugs and then elephants. I see we only have one elephant.
Yeah.
The elephant in the room, which is not in the room. Because people
I have no idea. I believe. No. I think. Yeah, I think you started a little bit later. Sorry about that. I would have like just like go forever, but Emily, I feel like so really hardcore with other people.
Well, it was gonna maybe. Participating in these discussions. I can leave them up, but I also linked in the Slack.
I don't know.
I'll show you one. So there's one really corner is like a mirror. When I was doing all the use and distributions of
Do you want their group discussions?
basically shows this is the rotation rate relative to synchronous and the orbital periods. Basically cover
Like, I can say what I remember, but like, without, like,
different initial rotation things. You see the so
what I do know is that
okay, so this makes a big difference. No rotation. So this initial critical breakup, the initial rotation.
there was like a factor.
They're all unicorns? Yes. So what we did is I was following the output certain things was one of the
Stuff like that.
No, dragons is
Using both games, we have stars that are very
different tidal prescription. Because we have this kind of
Circular case, because it was supposed to reduce to like the standard equation, and it was doing something strange. Yeah, and this was when we were trying to use Funny's equations, why isn't it working? So then after that, we were like, oh,
Are you going to want to
And then he walked away.
not like
What was that?
One thing that is
Come around.
Is it like
I need the 500 cross example, and it's.
I mean, I think like calibration. Yeah. And just hope that the stuff that
Oh,
right ones.
okay. Oh, wait, is this eccentric?
It is eccentric.
Yeah.
You know what?
I was gonna say, you like this.
I know. You're right. Sorry, I'll just say,
I guess there's the ones on the Hayashi line, like the giants and stuff. That show that you don't have perfect circular rotation, but it seems you need a whole lot of angular
yeah.
But we are only focusing on one.
That was what was motivating.
There were 5 questions within a question.
I'm gonna find this one.
It's like an enhanced Taylor Sprout.
Azure.
Oh, yeah.
Azure, I mean.
Yes.
I can just put it up if that helps.
Yeah.
Where is the link? Which channel? That we can use for every start the same.
So actually,
I have opinions of both
doesn't really affect
accretion disks and spin up.
you change the orders of magnetic field, the free factor.
Oh, yeah.
You get self-regulating. Now the thing is, if there is a differential rotation, it will create this magnetic field which
I think some of these are a little bit obvious for subject mass transfers, like are there new modeling approaches needed? Yes.
Like,
What do you mean? But I think, so I think it would be very helpful to discuss why, like what is the current state and what is missing?
yeah, I mean, otherwise it's always a solid body, right?
Yeah. So I think it essentially gives you
I
solid.
have one thing to say, I guess. So Adrian has this eccentric rotation.
In sequence stages, it becomes a bit trickier. And there you do get.
Are you already on the Slack channel for that base?
Oh yeah, Kevin.
Yeah, there's a Slack channel.
Also,
Yeah, we should. Should I take
I
notes?
have seen it in some model.
then it's harder for you to run.
Yeah.
Well, that's fine. I think what Joe can explain the things that I was
Think about these rapid mass transfer phases.
By the way, it's
More or
not
less,
correct
you
what I
change
said,
the
Adrian.
rotation profile of the star sufficiently fast that I would guess is a competitive effect versus just luminosity.
The Phil Davis is.
I guess with regular stellar evolution, it's just a very small part of the energy.
Well, so
I feel like 10% of the mass
So that he did pretty crude and thinks that that should be.
at Keplerian, the energy magnet to fully dissipate all this rotational energy.
But one of the.
Never negative.
I see.
Yeah. So that's something that I think no one considers.
Like a sub question I have.
You should expect some form of
Is that a good assumption?
whatever the process is, there needs some.
Often model mass transfers.
But it's totally not obvious.
But I
How,
just seems to always never happen.
it used to be kind of the idea that if
All right, how much of that goes
the atomic timescales are similar, and then it's maybe.
I wonder, I mean, in a sense, you have
So if you're like,
an initial situation where you
well,
think
yeah,
all
that's
this
kind of like the
material
other
is
thing,
on
right?
top,
That's
but almost
what,
Keplerian, or it cannot be Keplerian,
But we would want a general thing that
if
can.
that propagates inwards, you have a different energy, total energy. Whatever the difference is,
Stable versus
somewhere.
systems.
More or less we conserve angular momentum, but not energy.
But he
So
observed all
we
of
need
these
to put it somewhere.
period systems, and did all of these music
So that's
calculations.
definitely something we
The
don't
thing
account.
that came out is that you
energy
do have
conserv-
relatively equal
conservation
mass
considerations.
systems. So your primary is between like 1 and 1.5 solar masses, and then your secondary is a
Initially.
little bit initially, and your secondary is a little bit less.
therefore serving momentum, so you don't need energy.
And your orbital periods are.
Well, it's just a different distribution of angular momentum.
And then he found
So
that
that's
the
just
way
I
that he
omega
managed
is your angular momentum
Yeah.
for each layer.
out is
It will not give you the same total energy because that's omega squared I.
Yeah.
that kind of makes sense for
So-
elements. stars because
And
they're
then
not
you
that
reduce
mostly
it and conserve angular momentum.
range. And so if you want to make
And
it stable
you were essentially trying to sink to a lower
very early
speed,
on or
which
very
would
late,
be,
so you really need to have
solid
it non-conservative. But I think that's a very different scenario than for like massive star regime where you have more stable mass transfer.
yeah, no one considers that. Something actually I think I never thought about.
What are they now? You said they're initially.
Probably the energy budget is not the great.
Now, what are they observed as? Okay.
Remember this, that you
I
would
saw this in some papers that Patrick did, with Norman.
There are a few hundred days, I think.
Reading like.
days.
And then I-
Isn't that common envelope like?
That's what I said, they're only because
There's like repeated these.
these are like wide orbits, so they
Up here.
started on the
My
Earth.
expectation would be that this would make all problems worse because it would then to close your stars.
Yeah.
The closest star would have a lower critical rotation rate.
Initial orbital periods were like around when the
Then you go
mathematics was
easier into this
less than 8.
problem regime.
So
But yeah, I said it before, but the thing that worries me in Adrian's
So the
model,
point is that
it's
we
not
can
so
find
much
that
the
very
level of
number.
conservativeness, like all the binary calculations in the 80s, they started with conservative mass transfer because that's where you start,
I mean,
right?
it's not like a huge variable.
it's
So that's
manageable.
where you start, yeah. But it works with other assumptions that you have to take
We expect the
together,
physics
which is
to
that the
operate
mass
more or less
ratios,
the
that the model is only valid for mass ratios.
It's
that are
not
very
like
extreme,
calibrating
so in paper it
overshoots.
says
We
Q
see it's
much
more
larger
like
than
an
1.
adult model of how far you
Yeah.
go from the
You
convective
have to be
envelope.
larger than 10
This is
for
really
this.
accounting for all the physics, like the composition profile or not.
Exactly, so there's, I think it's not only the conservativeness that is missing, but it's just the approximations that Adrian had to do in order to even get a model out.
Problem,
It just requires
which
more
is
effort to dive into it and look more.
Dr.
into
Young Fei, right? All of his, or Will, any of Will Scholl's models, right? They're massive star models. They're way more inflated.
I mean,
than
Adrian later, like, I
Mesa.
don't want to criticize it, but because
They are?
like a really good addition to the model that was that.
There's
Just one more step. And
a lot of people.
But there are papers that do things
Some
to
of it is
conserve
that there's
mass transfer, and they're all in Slack
sonic
channels.
turbulent motions,
Right?
and so
That's- yeah, I
turbulent
mean,
pressure
we-
actually lends
Got
itself to
some
a
of
lot
them
of
already.
support,
highly
which does serve to
The only
extend the
problem
envelope.
with the Sopolo is it
Some
doesn't
of it is
close to
like
low eccentricity.
what you want to call
They use like delta just at periapse.
right, but yeah, they are.
As long as you
Then
quite
we can make small.
The radius of like
And then
I think
one
just pull up-
observation
I think that
that's
was
something
what-
like 2/3
Yeah, I
is
guess
significantly farther out though, isn't it?
Yeah, but you have to, what you have to be careful with comparing young phase models to Mesa models is
I feel like Adrian always wanted this.
or what you call them.
He wanted it to like collapse.
Because it's true that you inflate relative to a Mesa model that
Do it as a
favored the 3D simulations with, but to say that that is a 3D simulation
The
of
delta
that
function
Mesa
helps
model, I
you
think
because
is a
then
little
you
bit
just
misleading. So it's true also of the red supergiants that when we
Otherwise
put in
your
the
knowledge
red
base
supergiant, it was sort of.
Otherwise, it's a Gaussian or whatever.
Thing, it becomes 800 or 1,000. Actually, the two red supergiant models in
No,
our
I've seen papers that do that.
were both based off the
Is it
second
delta
Mesa model,
function
that they have a kind of 200 solar radius difference. And some of it is because of the way you drive the inner boundary. You
Yeah, so
really-
one of the questions was,
Like a-
does ever increase
conditions at the base of a Mesa model, or at the base of what you call the envelope.
eccentric
And
mass
then
transfer?
you actually construct a completely different solution, which is pure radially stable. You then let the thing run until it reaches a steady state, and then it becomes its own structure. So
Configuration? Low mass.
I would say that I'm not too worried that the radii are extended based on against the Mesa model, except the contribution from turbulent pressure, which seems to be.
That's more, that's a baseline
robust in
increase
physics.
though, isn't it?
That,
Because you don't have
that's
to.
baseline.
Mass ratio.
It softens the, yeah, it contributes to hydrostatic
From a
equilibrium,
circular?
so it softens the steepness.
So even just including from the Bill's analytic modification, that would add turbulent pressure, or let's say TDC.
Mostly the wider ones.
I don't think this is the way that you would want to do it. It's the way that you
The
have.
turbulent kinetic energy density in
I was
TDC
just
kind
thinking
of
wider
maps onto
because
the turbulent pressure in
Right, yeah, tied
the 3D Euler equations, but not completely.
All this.
More of a characteristic velocity of transport,
Implemented.
same as MLT. It's a proxy and it's better than doing nothing.
Effects like the eccentricity. But you'll just have a a bigger star, which is gonna lead to.
But yeah, this question.
Oh, but you can crank, I mean, if it's a convective envelope, you can also just crank down the mixing length or crank up the mixing length and you recover your radius. So two things happen, right?
For
You find-
identical physics, right?
Well, so I mean, here's like, yes, but like if you look at, say, the 3D red supergiant, we find two things. One is we find an inflation of the envelope from turbulent pressure. We also find very high mixing length alpha.
The way we calculate mass transfer.
And so those two effects, if you want to ask like, what would the radius of this star be? It's unclear that there's an obvious systematic difference.
Orbit average mass transfer.
Just from these sort of mass radius.
Scratch it over the orbit.
The better thing to do for that is
And then
look
what
at
do you
nature,
solve for
say,
the orbit
what are
average
the
mass
radii of these
Let's
stars?
just do what we normally do in binaries, right?
Yeah, just.
Whether or not that makes sense at all.
This seems like one of the oldest issues.
What are the video of the stars? I
How
find
about
approach.
then,
studying more deeper with the Wolf-Rayet stars.
I think,
much?
Really tricky.
I think they just
Less
lay out the
familiar.
theory very nicely and then.
So just maybe I can draw.
I'm much less familiar with
Okay, you
the
have
assumptions
this,
that they're making, the limitations of that model, and it's way
It's
older.
a function of R over R star. They have some definition of what they consider to be the
I think this is implemented.
You can plot the velocity. So normally is the typical model you would have is that you have
Yeah, bin star, bin star.
rows.
Yeah.
It's Leno's CS.
You're out.
Yeah, there's.
So then essentially what's done is that you have this beta velocity loss.
But yeah,
Form for the
I don't remember how it in the paper described how.
Okay, this goes like this.
At
And
different.
at some point within this atmosphere model with a given
But the
velocity
whole
load,
setup of the
they-
oscillating orbits is
that
the
we
same.
call
Is there
2/3.
any limitations to it?
The problem is that actually driving might not operate like this. So
Unless
you
the
had some
superloop
simulations.
spins
So
tomorrow.
Luca Bonatowski in Kyoto was working with this. Actually, you might have some initially driven outflow that then stalls and potentially slows down.
I think it's just.
And then you have this kind of behavior.
Wow.
So from observations, one issue is that actually
This sounds like it was just to implement.
you're limited in terms of what you can feed into an atmosphere model.
And now I
If
don't.
fair, like draw this line in here,
What?
and more or less assume that there's a photosphere over
Like
here.
what?
And
What
that
is out
the
of those
hydrostatic surface lies further off. So
That's-
whenever you have this optically thick outflows,
Everything always like goes back.
when you're approaching it from limit, it's
And then
very
prior to
tricky to
that,
say
there's
what's the
like-
surface of the seeds.
And the surface, right, exactly.
Yeah, know how to say it quickly.
It's even hard to identify that in the 3D model.
Yeah, halfway, that's.
So you were talking about the Tau 2/3.
They, and I.
What's this
I
for
think
an optically thick outflow where we're actually talking about the
follow on
more or
from.
less the photosphere that's
Modifies
in the width or
I was just thinking of,
Like it
of
reconstrains.
not, I wasn't thinking about any optically thick.
but I mean you're thinking about a 3D simulation where you compute an optical depth, right?
Yeah, it's just an average
I
optical
think
depth
that it might be that.
over the.
Okay. But you could in principle be taking finding the photosphere lies in the outflow already.
I know it's like.
That's
high-
So I can tell you you mentioned Will's models, phase models, and these models. So for Will Schultz has some models that are kind of local patches of blue supergiants, like 35 solar masses or so. There it looks like the tau equals 1 surface is kind of in what we might
When he
consider the
came
star.
up.
In yon phase, Wolf-Rayet, or not Wolf-Rayet, LBV simulations, then the photosphere is generally out in the optically
I
thick
understand
alpha.
where Adrian's
So
frustration
here,
came
there's
from.
sort of-
because
if you just calculated tau along various lines of sight, which
Right.
because it's very inhomogeneous, that may or may not be the way to do it. And it turns out that like
It's just like
how
a-
you do your averaging,
Like,
is what you call your
it's
average
similar
to get
to
you
that.
a factor of almost 2 difference.
So those equations don't call the photos. They don't like that root.
But that seems to be a lot more heavily into like sort of
Yeah.
wind in that diagram.
Whether or not the delta function's like getting worse is another
The
question.
red supergiant,
But at least
one thing that's been done in getting this quantity from
NASA knows how to adjust.
in other simulations, like some work with Andrea Kimas and
The F dot, right? So the F dot's not gonna like.
is to instead just take the luminosity leaving and then just take, L is 4 pi r squared sigma t to the 4th. You get your average temperature, you get your luminosity, those lines
Problem
kind of
that
cross
somewhere
at
in the
one point,
equation
and you call
divided
that
by
the
E.
photosphere.
So that was the problem,
So
right?
there's, it's even just saying what you call the photosphere, especially in this really inhomogeneous surface, subsurface convection, is already kind of.
I'm trying to understand, because in the low mass regime, it seems like literally all the posts.
And I think
this
is
mass transfer.
I think it's a fairly, so it's
talking
a,
about like mass.
Yeah, I think above.
it's a general, I'll say the problem is general.
So what we think
when
underwent
the
at least partially
or when the
stable.
three convective
So I was trying, we were just talking about it in the massive or intermediate mass
So,
regime.
and especially
stars,
large
right?
scale.
BE
So
plus
if
stars, they're all
It's
all of
a
them are circular.
simulation of the sun,
So
the granules are small,
anything between
fluctuations
weeks
are
and
not
hundreds
too
of days.
large, all of the turbulence is very
Stable mass
subsonic.
transfer, they start.
The fluctuations go something like the Mach number squared in
The tides
classical
circularize them.
turbulence, and so you don't have to.
Even-
The tides efficiently circularize them.
So like if we're doing the sun.
So they started very circular on tight binaries. These mass transferred towards the end of the main sequence and.
Yeah. Because it's not
Maybe.
that how we showed earlier, if you like squint your eyes a little
And
bit,
not others.
believe yourself that at 100 days, the spread in
But for
eccentricity
these, for the more massive stars, the really luminous ones,
4 days.
there's just so much more luminosity that the convection has to carry. And the only way to do that is by
So
driving
maybe
really,
The more massive stars at a shorter orbit.
velocities relative to the sound speed.
Or at least the population that I'm
Larger
thinking about.
inhomogeneities, these inhomogeneities
That's
that
interesting.
really
But there's
shape
one
the
question, right? So
surface.
do these
Even in
systems
stars where you
start
call it a
mass
radiative
transfer
envelope, but there's
orbit and then
subsurface convection zone where the
Or
velocities are
are they-
large,
do they
even
start
though
mass
it's
transfer
MLT
regular orbit, and is
stable,
there
on either side of this convection
afterwards,
zone.
because all of these
That's a
other-
condition on the acceleration.
we were gonna know
Conditions at the surface that.
Yeah,
I don't even know.
like the circumbinary
Do a
disks
mental model.
and
I don't
the.
know.
But there are like, I
yeah,
mean,
I'm
those
gonna talk about it a
mechanisms.
little bit. I'm just gonna talk about,
Really
like,
far,
various
and I can get like a little ejection of material, like a profile like this. And then I ask myself, okay,
really,
but how do I communicate this? Like, is the surface here? Is this something that's just gonna leave? And then should I just place it inward? Well,
Those are all mechanisms
I
that
don't-
would work, even if we have the old school circular
One
mass
thing
transfer.
we're exploring with
It's like
so
something
they do a bit of
extra they put on top
is to try to construct
of, like circumbinary disks.
of
that,
the photosphere deeper in, but we have an atmosphere more on top that tells us
Yeah,
what's
so I guess you
happening
can have
outside,
less
and says
tides.
what mass.
There's not so much from
but the
France.
way it's my instance of a hydrostatic atmosphere.
Yeah,
So
so
it's
you're
like
essentially
you-
putting your Eddington gradient at just a deeper.
Yeah.
So
So if there was
There's like one mechanism,
any
this kind of
slightly
like
better way.
grazing envelope thing from
I guess it's more or less going back to the subject of the workshop, which is mass transfer, but it's because it's important, so I'm not sure people are working on.
that suppresses the tides.
But
But it doesn't
nature of
the
that.
eccentricity, it just stops the eccentricity from it. And then I guess rock is up has these like natal peaks in white dwarf stars.
So let's go to very low metallicity, let's say solar system, for example, where winds are not that important. What we see is that.
You don't have all of these eccentric systems don't have white dwarf stars.
But as we keep going up in mass, we actually start seeing the disks, the tons.
Yes, otherwise you would have-
forward rotations.
Yeah.
Now to the point that we have like, the dams happens here. In these modes.
But then again, there's
They're
also like
inflated.
the-
We're predicting that all interactions for these very massive stars, for these
explain
global
like
50
the-
solar masses are gonna be K-safe, they're gonna be main sequence. And that is potentially very wrong.
How strong of a.
Okay, so it's just like a computational artifact. It's not actually what's happening.
So it could be that essentially from these 3D models, that essentially you're considering the motion of the material. That's why more or less my impression was that the media are actually more or less.
Wind mass loss.
You still have some inflation.
Wind mass loss, not mass transfer, is avoiding a lot of difficulty.
For this structure here,
Both
I wanted to put as an output instead the effective temperature at 99% of stellar mass.
Yeah, I was thinking that high resonances with high station.
For most of the evolution,
That's
yes,
crazy.
it's much more compact. But
Okay.
at some point, if the Eddington factor is really high, there's still a significant amount.
It's complicated, but I don't think it's like, oh, no.
Rising here in the Hayashi line,
Yeah.
it's like the Hayashi line means you have a lot of convection.
Yeah.
A lot of masses in
Yeah.
convection.
Ah, I see. So it's not okay.
So yeah, during this expansion, then that's right. But once you hit essentially hydrogen recombination and you develop this, this has a large chunk of convection.
So I think
But also the thing is that this sets where we interact, but also we have no idea about the response of such a star to mass.
yeah,
So I don't know if we could put within the 3D calculations a binary there and make it even more complicated to see how mass transfer operates in this higher. So I think this essentially has a large impact on.
Well, for the record, I mean, I get the same kind of impression for us.
I can imagine like the moment at the conference that you mentioned that 20 years ago and everyone was like,
14, 16, I get
idea
this
from
impression.
It's extremely sensitive to mass
Yeah.
loss rates
Yeah.
and overshoot. So essentially, if you manage to strip the star or mix it very well,
Yeah.
it behaves like a helium star,
Yeah.
and those remain hot. So that's another thing. So one other issue in here is that we have observations, sometimes especially which is the gravity.
Yeah.
So we're bringing a whole bunch of stuff populated over here. It's not
all of these systems.
not entirely clear if it's just low number statistics or we're not sampling the right metallicities.
What's done in Hobson?
I'm more and more starting to get convinced that even at very low metallicity stars would evolve like this.
The binary to be certain.
They would be very well mixed,
With the
not from rotational mixing.
Okay.
radius.
Yeah, I was about to say that.
Magic non-rotational mixing
Okay.
processes.
Yeah.
It's basically, if my intuition is right here, this can really help. My normal idea is that if you don't have any nice, MLT formulas like you'll get this data, I guess. You basically turn on something like that reduces the opacity effectively of the envelope. So for the engine, the star just doesn't.
X-ray binaries, I think, are cute.
So it will be more blue when it's really.
Also,
Okay, well, if you believe my story time, then I spun.
Go to the right.
Yeah.
So it's like, so somewhere in between,
Those
the reality is that you probably don't just
I don't think it's
inflate
crazy.
the envelope like in 1D. You get this turbulent convection that's probably more efficient
I don't think that they're all.
at transferring energy. But
eccentricities
still
of
doesn't
BE
really-
binaries?
Well, you said they're all circular.
One of the
I
things,
meant BE plus.
one of the things
yeah,
Mesa isn't really doing
X-ray binaries
self-consistently
are tend to be.
is
BE.
including this pressure term from the turbulent energy densities and especially schemes like MLT++ or the superad reduction just are sort of pushing flux around, right? And so when you push flux into convection, maybe you call that a higher convective velocity.
so is it
In
that
nature,
more
that's
related?
probably what's happening, but the larger the convective velocity relative to the sound speed, again, the more likely it is that your turbulence is
We argue that
larger amplitude fluctuations, and then you have.
is there any new observations that will help this problem?
This is a pressure term, stress energy tensor.
So Will has.
Yeah, Will has a.
I mean, it feels like to
basically
discern between
implementing
is different if it's pumping.
all of this in,
if it's not
and it's
pumping.
like,
It feels
I
like
guess
it
it's
would help
almost
to
there.
Yeah.
manage the differences in the population.
Will, yeah, I mean. Will
You
knows
you
the
mentioned
data
that
reduction for Roman.
BE
Yeah.
plus binaries
Halley has a more
maybe.
stable-
I've been
because they
hearing
started
from
off
Matteo
circular,
promises of
right,
having this
well,
calibration stuff.
right?
Decade.
Yeah, I mean,
That
Mateo's.
comparison,
one of the
I
guys
think,
who wanted to go, so.
What he did, because I feel like something could be
But their
done.
differences
Yeah.
are,
Unfortunately, Adam was.
they're not all subject to the same mechanism.
This
Put it in
is-
the code.
Well,
so that-
we don't know what all
So let's wait to see what was on.
Yeah.
We'll transition.
2017, so there's
Yeah.
more
Right.
systems, but it shows
Right.
different.
Some of Will's
Similar
implementation is based on this sort of pseudo Mach number scheme that works in the regime that he tested it in the models that he has.
Better much more.
comparing, the more broad you want to extrapolate that, the more uncertainties that lies. It's kind of like winds in massive stars too, like, everyone you pick your observational data set.
So the difference. I think we're getting a little bit here as far as the ladybug topic. Should we maybe zoom out and think about addressing the big picture questions that were posed? Magnetic fields, Pablo?
So what are the errors?
Like in my master's.
So I have a big picture question about binary evolution. I feel like often we use these sort of secular average timescale things for wind. Does it matter if the wind process is actually a stochastic bursty thing in a binary?
A little bit more like the.
Of course, pulsations, right? Drive things on some shorter timescale.
So I would guess if it's really stochastic and not phase dependent,
I think it's kind of nice that we
average
don't see these.
average out in a sense. And period of time really average.
Is there any currently in the recipe?
Yeah,
it seems like that one is our
known and are eccentric.
Yes.
Okay, because
Yeah.
you can use a time average radius
Okay.
relative to a rush. Right?
Yeah, I guess that this plays a role in like very late evolution, so like Mira variables. So you have
So we have 5 more minutes for the discussion.
oh, the star is changing enormously.
Oh, okay. Forgot about that.
What observation is Gaia gonna help?
Regular
Observations we need are in the long run.
the oscillations are usually at lower
Maybe tens, days, hundreds, thousands.
I tend to have the feeling
But
that
those sources
are more
are already in
very
the.
valuable information rather than something that
There, not across all masses. I mean, I think the Gaia.
Do we have observations of pulsating versus overflowing stars?
we have actually quite massive
But I think
heartbeats.
DR5 will help.
Oh,
So there's for
More
instance,
five.
we'll study 30%.
Well, 5 won't have everything.
Okay.
I think about
Yeah, probably
calibration,
things
but what I've heard is that the heartbeat
We're
signal
gonna help with
is
the
extremely sensitive
slightly longer baseline.
structure of
The,
so you might be
because
over.
of how they're doing the, yeah, there will be EPAC astrometry, but also
I
it's how the
think
main.
the issue with mass is that they have a lot of intrinsic variability. It becomes quite hard. You just have like red
That
noise.
they didn't understand.
That's what I said.
So they just kind of cut parallax SNR versus orbital area. And what that
Much harder
did.
to identify modes that are not just stochastically driven by the
500 parsec, right? Effectively. Plus or minus. I know it's
Yeah,
not exactly.
yeah.
So we're really gonna get the
Okay,
massive.
that's a
band
little
with the
different
low
than
mass
my
band.
intuition, I guess.
Low
about,
mass and
my sense of our model for like,
have like a.
what is the mass transfer rate as a function of this?
I think we could, there's probably a
Delta
lot,
over slope,
like I think.
is pretty sensitive. We have sort of some prescriptions that exponentially ramp up, ramp down. And so if you like really start pushing stuff, 1% past.
I had,
All of the 1,000.
while you were presenting, I had a WhatsApp chat. with
Really get a
Sahar.
different
Yeah,
answer.
she's showing your plot. And then he told me, I don't believe any of the eccentricities, they're all bullshit. But then you actually said that you validate many of them with spectroscopy, right? So they're not.
Yeah, I mean, at least some of them, yeah. They're actually pretty good. Running the he is giving a 4.7. What the problem is that we actually have to consider is that this very super giant radius.
Okay, wow.
That means that tells us is well, at least some of them defined by tau equals 2/3. So which
That like
next
bothering me
that
is
of extended atmosphere that might
Like
exist.
if we can get absolute rates.
Can really influence the mass transfer. Because this, even though there is a little material in the
Working out
atmosphere, it
uncertainties of
starts
mass,
to
like stability, for example, like which one should
get
be
extended again, and then it will lead to more mass transfer, and this is a
like
vicious
Kareem
cycle.
said,
So I think this is a
grabbed like a
big
bunch of
urgency
sequence
model.
binaries and a bunch of white dwarf sequence binaries, and they're not
What if you do like an identical
sequence binaries, that there's two big bumps that are more in orbital periods that are due to
you relax it?
there's a
like
dip.
that would Because I feel like that could cause.
Then in the white dwarfs,
Well, I'm curious because that could produce
where there's like brush over
I was just gonna say, or how sensitive
way
would that be
the
to
one
atmosphere?
and there's a huge wide bump as well from like non-interacting but wind mass loss.
That'll change
We can get the relative height
the
of
functional form of the density profile.
bumps and the relative height. of the wind
By
mass.
relaxing it too, then you're
And
basically kicking it back into the mesa solver. So you want the structure, whereas like when you just
Almost,
adopt
like you could
the
almost.
atmosphere model, you don't have any of the hydrogen.
This is where these things are going. Now let's focus on this.
I'm agreeing with you.
yeah, no, but in principle, the way these calculations work is that you're integrating through the overflow layers.
Like regimes, you also get clusters.
You have extended layers, but they have very, very new.
You're making your slide, we've got like
Things are eccentric.
minutes left. Just
Oh,
giving it
we need to
time.
make a slide.
Yeah, Evan and I have been.
Feel free to help us or whatever you need.
Yeah, you do have systems.
Yeah, we can.
Systems with eccentric or have very small eccentricities, so that's
Baby systems that
I do like this more or
You're
less.
making your slide.
It's the red supergiants, the atmosphere is very fluffy.
Yeah.
So we can also get
That would be tough
a
to
lot
do.
of overflow when we have like formally loaded overflow.
Unless it's like mass ratio.
But indeed, this atmospheric
We all have to like start that.
loss design or that kind of environment, that's, you don't deal with it.
But I mean,
What would be better?
I don't know what I'm showing. Is it showing us how to do better? You know?
That's for the high mass X-ray binaries. I plot onto the mass ratio and the SA
It's essentially broadens enormously the range of which.
Yeah, indeed.
of the period. So a good start is that we can pick up
It's a set of internal assumptions about the structure of the atmosphere, right? And then they map that onto like, somehow that maps into the radius of the star, and then, there's a sort of subgrid model essentially that may or may not be consistent with the actual stellar model. So, yeah, it's hard to.
For most cases,
Yeah,
we're underflowing, we just use a Bernoulli equation to move from the surface to the Lagrangian point, and we assume isothermal atmosphere. Well, atmospheres are not isothermal. It's a very bad assumption.
It's not enough, right?
Yeah.
Then,
It's also, it is true that a lot of these.
we just mean that some of these would make it
Sort of simplified assumptions that.
Oh, yeah,
approximate
see
conditions at the surface of the
the
stars.
dicey are not able to circularize them just yet.
How do we get around that?
yeah, two group
Doing
one's
this.
longer than.
Well, I don't know if we can construct it as having a more general atmosphere model. I'm trying to do similar, like these Bernoulli calculations.
But
Eventually more.
I have also one question for massive stars. That's easy to imagine, but for white dwarf binaries, what's the reason to cause the eccentricity?
One thing that I'm not sure I understand is that
Those are
giant.
kick in the
Let's say that.
Enough in the widest orbits.
In the wide orbits, yeah, and it depends on the, I think it depends a lot on the facts of the system when evolving, so it depends like on the phases, evolutionary phases. 2 minutes. But the higher mass you get, then the less likely you have giant branches.
So essentially, whatever material you remove, you cannot just cut a star and the star will
No,
be happy.
sure.
So it essentially feels bad.
Yeah, but okay, but this here.
We have 2 minutes to write down your ideas. Oh, no, it's on the.
See, the pressure scale height becomes comparable to the radius.
Yeah, I'll need an extra.
And you can have a meaningful fraction. In your total main sequence, your pressure scale height is like 1,000. It's the giant, it's
Yeah.
Assume we have a circle.
more the distinction of like formally keeping the rods would be
30% away from the roadshow. There's still a lot of. Yes, I did want to say something about this. In an earlier paper that we had with Gio Miru, found that because of using correct initial distributions for things.
Yeah, but
basically it's the most important thing to find the distribution of eccentricities variance in clusters.
I mean, if you extend it
And that
more.
even if you enhance tides by a factor of 1,000, the change is not dominant over using the correct initial distribution.
Okay,
Like little.
I got it.
So everything above.
Not going to be anymore.
Basically, 10 days starts quite eccentric, and all the bullshit shows basically in that regime where they already started something nice.
So we can take some kind of a coffee break maybe in the afternoon.
There's one extra thing to care about, actually using the correct initial systems that we see might not have been led to be eccentric by some process. Maybe they're just born eccentric states.
I have a lot to say about mixing. Extra mixing session.
Systems that this would go for.
Well, we could start with the
that basically resolves most of the eccentricity period.
we can give them like another minute. We just need to like summon people inside.
And that's definitely the dominant effect.
Do you want me to do this? I'm
saying, how does that
Yeah.
extrapolate on my level of the time scale?
I've got a whole stenographic version of
I may actually discover this was.
Oh my god. And suddenly you see the light.
Yeah, so the thing that I was wondering is that slightly more massive stars.
I think you might be able to get the orbit, but that's the whole problem. Like, there's so many
lights, and we're right about it.
Oh, I saw you put them in scenario.
I think get all of our text to fit on like the slide. Why is it like so small?
move from there to
Crazy.
maybe everyone.
That's not what I want.
Because they're so, fast, so high.
They're not.
And then for compact optics, you can definitely get.
Right, that's right. We had this discussion.
Oh, sorry. Oh, yeah, right. Yes, so we can do a chair for that. I agree. She did also just look over. So.
Process. We'll just, I'll start it with the discussion. Okay.
Okay, have a seat. Let's get started.
Oh, yeah. Should I talk? You could talk. Maybe it's not in this slide. Okay. I don't mind.
Ding, ding,
Yeah. Like, I just don't want to.
Just try to summarize what we discussed.
All right, welcome back. I hope you all had a good discussion. I know time was a bit short, but I'm glad that hopefully it seemed like a lot of people had some good thoughts on the topics. The slides, people are working on some of them still. Question 6, nobody voted for, but I think that means that we need to reach out to other communities and try and understand what they do. But that maybe is a problem for another time. Okay, so do we want to start with the first? Or we can start at the end.
You gotta read, but like in 5 seconds.
Okay, so let's start with the question number 5. Let's go to the end.
You just refreshed now, it's.
Oh, is it ready? Okay, we can have one person or a team. You're welcome to come up if you want, or you can stand there. I'll time 5 minutes to present your slide. So group 1.
Oh, yeah. Good? Yes.
Okay, go for it.
Are we gonna put the slide up?
Yes.
Okay, yeah, so eccentricity during mass transfer, there's definitely a set of models out there. We found a whole list reaching back to the 70s or 60s even. They do apply approximations, but we have found some that include non-conservative mass transfer. I think the biggest issue is most of them seem to deal with the mass transfer rate calculation in the delta approximation, and that's something that's probably valid for very eccentric systems, but mildly eccentric systems not so much. In different slides and different resources, we have found that there's a whole bunch of eccentric systems, carbon-enhanced metal poor stars, the barium stars. They do all contain systems with eccentric systems. But a side note here, we shouldn't confuse processes that might make them eccentric with their initial eccentricities. There's definitely a whole population of longer period systems that are born eccentric, and there's papers on this. It might make it even more difficult to estimate what the effect of this eccentric mass transfer is. This is indeed something that is seen over a large range of masses with these systems, though. Observationally, Gaia will help with this. And there's some catalogs that definitely will help with this. Right, and indeed, I think if we combine our powers, then with population synthesis, we can do quite a bit, because many of the other eccentricity inducing processes are in there, maybe tides, maybe kicks, these kind of things. And if we have a code that includes all of these non-conservative stuff and non-delta function mass transfer rates, then we could try it with different population synthesis codes. I think that would be a desirable thing. And maybe something we should start here and start making. Great. Okay, that's what I want to say.
Thank you.
Does anyone else from the group want to add anything? Anyone from the audience want to add something?
Yeah, question.
I'm thinking of the last line, like shared between pop synth, like in an algorithm of this kind, does it need to be limited to rapid population synthesis?
No.
Not necessarily, right?
No, I didn't write rapid on purpose.
Okay.
Pop synth does not mean rapid.
No, yeah, it could just be a package that's a repository on itself and includes a Fortran wrapper or whatever.
Yeah.
I just think of the averaging that you need to do
Yeah.
of the orbits. It won't work the same.
I just had a quick question, which is like, it says like eccentric high mass X-ray binaries, but so do we think in some future we can, distinguish eccentricity from mass transfer versus like kick and so on?
It should be different.
Oh, you mean so the eccentricity induced by the kick?
Yeah.
And the eccentricity induced by mass transfer? I guess that depends on how this mechanism induces the eccentricity further, right? There's definitely effects of pumping eccentricity in this. And I think we need to run models to see what the different distributions of this is. Well, there's some.
Yeah, and I suppose from the observational side, then it's going to be really helpful to have like good data sets where you have like specific types of systems and you observe like a substantial number of those, and where you start to have an idea where you would think that there would be a kick or not a kick or something like that. So I think that like getting, you know, multiple, like, and not like a small number multiple, but, you know, like tens or hundreds or more ideally of systems at like given evolutionary phases, and with given types of stars, where you can say like this population does this and this population does this, at least from the observational side. I think that would be really helpful. Yeah.
So just a comment on disentangling kicks from other eccentricity enhancing processes. I think one avenue I think would be useful is to, from observations, characterize the eccentricities of the progenitors of the systems of the high mass X-ray binaries. And essentially that's something that we need to use as a prior to any kind of inference on these compact object kicks. If we're using, for instance, B X-ray binaries to determine what are the kicks that they receive, we need to have information on the previous state on the eccentricity and period separation to have a clear identification. So at least that's a problem that potentially can be separated by understanding the population before.
That links a bit to the pre-main sequence that we were talking about, and understanding what are they born with, what's the distribution, and then what are the processes that either maintain eccentricity or change the eccentricity, pump it, circumbinary disks. But thank you very much to the first group. Second group, I forgot what these were. Oh yeah, those are the unicorns. Now we have the dragon. Dun, dun, dun.
Hi. So to constrain accretion efficiency, so first of all, there are many ways you can lose the mass from the winds of the donor. If the donor is very massive, from isotopic winds from the accretor, then if you have a disk around the accretor, say in case B mass transfer, then you can lose mass from disks as well. But fortunately, we have a lot of observations to compare models to, like, and they are kind of like dependent on mass a bit as well. So if you look at like 10 to 30 solar masses, then you have like strip stars, which are not Wolf-Rayet, but if you go higher up in mass, then you have Wolf-Rayet features. So, but there are a lot of observations we can compare our models to. And then there are some upcoming surveys that can give us much more data, to observational data, to compare these models to. Yeah. To get constraints on mass transfer efficiency.
Okay, comments, questions for this group?
Yeah, I don't know. Maybe I wanted to add that. It was saying that we have lots of observations, and because there are lots of systems that can give us constraint on this, but actually the number of papers that dare to give constraint and say, well, we put this constraint for this kind of systems are very small. I think I can probably count them in 1 or 2 hands, and and this is maybe surprising, or maybe not. I mean, maybe if we really start digging into this, we find that even if we have so many observations, these are not really that constraining, and that's a problem for the models, because we can come up with lots of models, but if we cannot compare with something solid, that's complicated. So I don't know. I'm a bit confused about this, but.
Other comments on mass accretion efficiency?
It's not a comment, but a question. I'm just curious what you thought of for the 5th item. magnetic field modeling? Are you thinking of donor or a creator, or what's that?
Maybe Brian wants to take that question.
Well, I was just noting that a lot of the all I was saying is that there's been a lot of advances in studies of accretion disks in recent years, which seem to show that the magnetic field that you feed the disk has a big influence on the properties of the outflows from the disk, even the evolution of the disk. So I was just saying that it would be good to connect these communities more. There has been some efforts along these lines already, but and maybe we should think about more boundary conditions for accretion to simulations that might be motivated by the mass transfer. So what do we expect for the magnetic field strengths that are feeding the disks from the stars, and maybe that should inform models for these accretion disks. That's what I meant.
Any other questions, comments? I mean, if you take the systems that we observe and you add up how much you think is accreted, and you add up the, do we see I mean, can you add up the material that's donated and the material that we see and the amount that we accreted, do they equal what we expect? I think it's hard to tell from the observations if we always see the mass that's lost in non-conservative cases. Do we always see it?
Yeah, how do we estimate this?
I wanted to, echo what Ruggiero said. I think there's just it's really difficult. Let me start with that. And I'm not an observer, so I don't know the data well. But I feel like if there was as much work into trying to constrain the accretion efficiency as there went into trying to constrain alpha common envelope, I think we would be much further in life, maybe. I don't know. It's a difficult problem, but there's individual points where we could learn something. And I'm also guilty. I didn't do anything. So, but it would be nice if maybe we put our attention more there.
Like an also. Other Matteo, you want
I was gonna say, what if it's exactly like alpha common envelope? Maybe a parameter we should not use at all.
Well, yeah, but there is a question: how much mass made it from star A to star B, which I think is a better parameter already than alpha common envelope.
And do we constrain that by looking at B and seeing how B changed, or do we constrain that by looking at the environment and seeing what was lost from the system? Like, how do we disentangle that? I think is both, and which systems, and blue stragglers I think are good.
Yeah, I vote clusters.
Clusters,
You have
because
the
they
best mass constraints, and so that might be a path forward, doing this in more clusters. I mean, the problem is you have to have extremely well observed systems to get all the constraints that you need. So, I think we don't have that many constraints because we need a lot of data. But if this is like a priority that we should have as observers to think about where we can get these constraints, I think I have some ideas about that. So it's good to know that you guys are interested.
Super. Thank you.
Yeah, I think if many of you are interested, then I also have a lot of algol systems that I want to look at. And they are like short periods, so we can get accurate constraints like masses and stellar parameters. Yeah, I'm very happy that many of you are interested.
Absolutely, because I feel like it seemed like for a long time, like theorists refused to believe that the objects we found were actually post-mass transfer, because how could you get stable mass transfer? And now the question is moving to like, well, okay, it's not conservative, so how much mass actually gets transferred? So it's kind of a new question, and one that I do think we can start probing with observations to some degree.
Super. Thanks very much. Group 3, I forgot what that was. Those are the octopuses, the octopi, the octo.
Yeah.
Oh yeah, there you go.
Yeah, so I mean, I think Pablo had given the answer to how do we get more conservative mass transfer. It is like coupling the disk to the star. The problem is that in 35 years, we haven't tried. And so what we discussed is like, what would be the challenges in doing this and what would be the trends. We didn't really converge on what observations would help in deciding between option one, which would be these, but we don't have option two, which is what we are most of us using when doing binary calculations. And that's because of the issues that we've already been discussing of it's difficult to find these systems. So actually following up on what you just said before, I have a question of, do you have clusters with turn-off masses that have radiative envelopes with these blue stragglers?
Yes.
Great. That I think those are very good data sets indeed to try to play with these things and distinguish these models, because the rotation rates of the stars and their masses will be different.
Yeah, so for the studies that I've been doing, it's like the more mass of a blue straggler you get, the harder it is to detect the white dwarf, which you need for like the best constraints on mass transfer efficiency. But if you want like a limit, like we could do limits just from what the mass of the blue straggler is and the turnoff mass is. So it's like we could certainly put some limits on this, if not do like very reliable amounts.
Oh, and in terms of what masses, well, applies to all the masses, and that's why these constraints are valid.
Yeah, so maybe adding to the cluster thing, I think Chen Guang is, she should have been here, but I don't know why. And, oh, okay. So she also works on clusters and binaries in clusters. And I think, remember from her talks, she was saying that with the accretion efficiency that we usually assume in MESA, so the rotational limited accretion, we definitely don't form enough B stars, for instance. And so that's I think already a constraint. So she was advocating for a higher efficiency of mass transfer or higher stability of the mass transfer. Sorry, I turned it off.
And when you spin up, do you get dynamos, magnetic fields? Like, should we expect these things to be magnetic? Does that then slow down the rotation? What's the physics there?
We did touch upon this a little bit. And if you look at systems like the ones that Julia is observing right after mass transfer, or if you look at runaways ejected from binaries that presumably have accreted mass before, they don't show any particular sign of strong magnetic fields. That doesn't rule out that during the mass transfer process that you have not observed, there might have been relevant magnetic fields, but it doesn't strongly suggest it either. Like Jan-Fei also brought up that in accreting neutron stars, sometimes you have the magnetic field that changes the accretion flow completely, takes mass from the disk, shocks it onto the pole, and then rotation is not a problem anymore. But that probably requires pretty strong fields that we don't observe. So this, it seems weird, like it seems premature to ask the question, what about magnetic fields? Well, we have plenty of problems without the magnetic fields anyway, and no hint that they should be there, I think.
So in CVs, there are things called, oh, this thing is weird, intermediate polars and polars, where they do exactly this. So it's neutron stars also, but also polars, and you literally launch the material onto the poles through these magnetic fields. What systems is Julia modeling? Sorry,
not modeling, observing.
Observing,
just
sorry.
Right after Roche-Lobe overflow with these strip star impostor things. Yeah, and Tomer, yeah, many people.
Tomorrow, not later.
So regarding white dwarfs accretors, I think this would not necessarily save us, because if you have a magnetic field and you have something like polars or something like that, you also have a much lower critical velocity, because now the critical velocity is not the surface of the star, but is the outer radius of the magnetosphere. And so you can go into a phase in which the star is not rotating very fast, but still the material cannot get inside because it's propelled away. So that may also make it worse in some cases.
Just want to like bring you guys another intention, like this one talking about like synchronization or like yes, some role about tides in doing this, because we usually think about like tides always helping with energy dissipation, which means we tap the orbital energy and put it into the star, and then lead to, let's say, orbital circularization and like alignment of the spin and like orbit, like doing spin orbit alignment and also trying to synchronize the star. Actually, there's a new thing, it's called inverse tide. I think, yeah, Jim Fuller posted this paper on 2021. Some tides can doing the opposite. They're trying to like transfer energy from the star back to the orbit, and then leads to like pumping eccentricity first, and second, like causing spin orbit misalignment, and also trying to do like desynchronize the star spin. So like with the orbit, so like, yeah, so like that doing some opposite like direction. So that may helps like, I mean, in like our traditional way, think like if mass transfer happen, we always like synchronize the orbit, like the star spin synchronize with the orbit. So then, yeah, affect some like star rotation speed, but like there's some, can be some opposite way for understand this issue. And also, yeah, this also depends on what kind of like mode you excited due to tides, like if it's a prograde mode or the retrograde mode. So that's, yeah.
I guess that would help in explaining post-mass transfer eccentric things, not that much in making mass transfer more conservative, or at least it's not obvious to me how that.
Change the speed.
Oh, you spin it down with the inverse tide and prevent reaching retrograde. Okay.
Okay, thank you very much. Let's move to the next group. Please.
Okay, then in terms of case BC or D mass transfer into main sequence companions, why do we not see them? And if we should, how could we see them? We first look at some systems that seem to match this class that we are aware of. There are two specific ones that we know, VV Cephei and Epsilon Aurigae. The first is a red supergiant with the main sequence companion. The second is a yellow supergiant with a companion that's hidden by a thick disk. So these are both eclipsing systems with very long periods, which I think are of the order of 1,000 days for VV Cephei and 10,000 days for Epsilon Aurigae. So what happens, we imagine happens with this kind of system, if they are out there and potentially observable, is that because these are very long periods, they're not necessarily, you don't necessarily observe them for more than one cycle. You generally don't observe them for more than one cycle, and so they're not automatically connected to a binary necessarily. And this may be associated to a different kind of source. These are also eccentric systems, which heightens the chance that they're undergoing episodic mass transfer, and that connects to the long periods. But if they are being specifically targeted, then maybe more systems of this kind could be found, for example, in TESS, LSD, or Gaia light curves. We don't necessarily propose looking for them in the X-rays, which we generally associate with case B or further mass transfer in systems with compact objects. But we did think about looking for more subtle signs of this kind of mass transfer. For example, in peculiar supernovae, where for example, the supernova occurs while there is an active episode of mass transfer. There's going to be a talk by Andrea, sorry, Andrea tomorrow on this topic. And also potentially detecting signs of mass transfer to the companion in the abundances, for example, in barium stars. But we do need to know exactly what to look for. So besides looking for a very long period light curves, we would also need to know exactly what kind of emission we expect from these systems, which of course necessitates that we have a proper modeling for the kinds of UV and X-ray emissions that we would expect. So
more models would be welcome, and then looking for this kind of systems so we can get clear predictions of what we are looking for. And also for more particularly for distance systems in mass transfer from supergiants, we have observed with ALMA that these are often very dusty environments. So maybe we should be looking for infrared accesses. And then this potentially is something that we could try to do with JWST. I don't know if anyone wants to add anything. Okay.
I can say on the modeling side, I mean, really, what does accretion look like onto a main sequence star from a giant? In 3D models, most people model the accretor as a point source, and it could be a white dwarf, could be it's just a mass. And I think that's part of the problem of like what should we be seeing for accretion onto these systems? So better models of that. Other questions, comments?
So just, you mentioned white dwarfs. I think this is actually quite an interesting regime because you have this these expectations that depending on mass transfer rate to a white dwarf, you expect very different phenomena. If it's too high, then you get that the white dwarf tries to become a red giant, and it can essentially fill its own Roach law. So I think what happens there is a bit of a mystery. And then you have this range of novae or stable accretion. So there's a lot of potential phenomenology in there that's interesting to study.
Other comments? I mean, in that case, that's why they invoked these, disk winds that can stabilize things. But I still think it's hard to see why don't we see the AGB stars and the red giants transferring mass onto a main sequence star, or do we? And it's only these really wide systems.
I think that you do. I think the hot subdwarf B stars have stable mass transfer from a giant branch star onto a main sequence star. Probably others as well.
Just to go off that though, like one of the problems we were kind of thinking about is, if there's X-rays, it's obvious that there's accretion going on. If there's a hot companion, like a very bright white dwarf or a subdwarf star, that's very obvious, we can find that. But are there subtler signatures that we could be detecting earlier on before the star is super stripped that would kind of clue us into earlier phases of the mass transfer? And I think we do see these clues, like with these eclipsing systems, they're really hard to detect because they're eclipsing every 10 years or 20 years. You get one dip, and only if someone sees this weird light curve and is like, I'm gonna dig more into this, are we getting results that's like, oh, we found an accreting main sequence companion around, a supergiant or a red giant. So I think there could be lots more of those hidden in the data that just like they don't have bright X-rays and they're hard to find in the light curves. But if we actually went digging for them and this like huge number of light curves we're having coming online, we might find like quite a few. So I think that might be an interesting route forward.
Maybe one signature of accretion on a main sequence star is just the fact that if you look at the 1D evolutionary tracks Pablo showed some in his talk, like the star will be bloated, get redder and out of equilibrium, the accretor. So it might not look like a main sequence star, like observers might not put the spectral class that corresponds to main sequence, but they were probably lurking in the samples already, as Holly said.
Maybe the ELM white dwarfs as well, some of them. The who? ELM white dwarfs.
Extreme low mass white dwarfs. Any other last questions? Okay, then we have our final group. Thank you. Ladybugs.
I'll go. Okay, so as we were convening, Brian walked by quickly and said, oh, this one's really easy. The answer to which uncertainties in stellar astrophysics have the biggest impact on our models is all of them. And then he walked away and joined some other group. or it's something else. And I think our discussion did bear that out mostly, maybe with the exception of winds. We talked a little bit about winds, and it seems like, at least in some cases, slow winds, you can maybe take a secular average and maybe things aren't so bad there. But we talked about a lot of other, things that happen during binary mass transfer. Angular momentum transport in accretors is certainly something that we don't always pay that much attention to. Very rarely account for any sort of heating and dissipation in those differentially rotating layers. That can matter. There was a lot of discussion of large fluctuations, particularly in massive stars on the high luminosity end, where I initially wrote in these slides that it's just impossible, but Jared deleted that and made it more diplomatic. So maybe there could be progress made there, but I think it's certainly a challenging problem if you want to go into the regime, probably, especially where you might want to do population synthesis for, LIGO binary black hole sources, for example. We talked about pulsations. I think there's probably a lot more to say there. We didn't even really touch on tides. And Mung's really nice talk yesterday has convinced me that tides and their interaction with pulsations matter a lot. And let's see, a few other things. Yeah, I guess on the higher mass end, red noise, intrinsic variability, and how that might interact with mass transfer from massive donors, also important. And yeah, then we had a really interesting discussion, I think maybe previewing a talk that is yet to come. I can't remember who it was going to be by, but what is the effect of the structure out beyond the photosphere? Because usually, for example, in MESA, we have some, Andrea, great, okay. Yeah, but so for a prescription in MESA, for example, right, we have some physics calculation that is done more or less independent of the stellar structure model, right? And then attached onto, what's the effective radius of the stellar model. And if you, start trying to take into account the different details of different types of stellar structures, especially if you have a star that has an extended atmosphere, that could really introduce a lot of uncertainties. So I'm really looking forward to Andrea's talk about that. And then we didn't really talk about this, but Pablo said there's a whole large discussion to have about mixing and how that interacts with mass transfer. And EB also said the same thing about opacities. He's been doing a lot of work on opacities. So keep an eye out for that, I guess.
Thanks.
Okay.
Just to comment, we do have extended atmosphere included in our mass loss. So, I mean, it is, and it is not just extended atmosphere, it also includes the binary effective potential. So it is taken into account for modified gravity.
I have a nasty thing. Like, these are individual ingredients that are uncertain and important, but in some of these physical situations that we try to model, shouldn't we also worry about treating these as independent things? Like, for example, okay, this goes into the mixing, but the example that I have in my head is that in MESA or in a stellar evolution code, you calculate the diffusion coefficient for every process, and then you just sum them, like every process doesn't know about each other. But then you reach critical rotation with a thermaline mixing coefficient that is higher than your meridional circulation coefficient, and they still don't talk to each other. That's a bit weird. Should we worry even more than the individual ingredients in how we treat them together when they come at the same time with similar amplitudes?
I mean, convection and pulsation is another example.
So I don't know, do you want to go? Okay, so I guess it's quick. I guess we shouldn't over rely on calibration. So I guess calibration can be useful, but we need to use it to inform physical understanding. So we're not just moving knobs around, but actually understanding what's happening. If we understand the physical process, in principle, we can think about them together in a very different regime. Ideally.
Yeah.
what I was going to say is kind of related to what Pablo said, and what Evan said. We didn't talk much about winds. I think we did in a few different ways. One is we talked about kind of the clumpiness of the winds and the time scales on which the winds are launched, and if they're bursty, and how that relates to the orbital period or some of these other things that that matter, whether or not we can kind of marginalize over that. Another thing related to that is also that, a lot of the sort of stellar wind prescriptions that we use, some of them are physics motivated, some of them are motivated by physics flavored, some of them are motivated by calibrations to observations, and a lot of times what we do is we'll kind of crank up the number up or down, or put in a constant wind or something like that, and because the wind and its evolution also then affects the orbital evolution, this can be a pretty important ingredient in this, and there's maybe an open question of how much, is it okay to turn that wind as a knob? Do we need new prescriptions? What should we be, what even should we be testing there? I also wanted to sort of echo something that's been said, or read something that was said in the chat, because Simon isn't here right now. But he said specifically regarding pulsations that this, for quote, for red giants, there's an upper limit of about 1 kilometer per second in RV amplitude from pulsations, depends a bit on the surface gravity, and there's sort of a stochastic contribution at the kind of 0.5 kilometer per second level. Overall, and that's important in red giants. AGB stars are a little bit different. So if you're undergoing Roche lobe overflow on that giant branch, when you're pretty luminous and your convection is large scale, and et cetera, then pulsations should be included. On the main sequence, the RV amplitudes are much smaller, so it probably can be neglected on the main sequence. And then classical pulsators are typically a few kilometers per second. There's complex relationships between pulsations and tides, as Mung told us a lot about. Right, gravity modes can be tidally excited, sap orbital energy, leading to more rapid inward spiraling. Thus, gravity modes must be included for stars bigger than 1.2 solar masses on the main sequence. And also, pressure modes can become tidally trapped in one hemisphere, but there hasn't, but Simon at least hasn't, and neither have I, seen anything in the literature about them strongly affecting the orbital evolution. But that might just be that there's some work to do there.
I would just quickly also like to add one thing, is that especially with the case of red supergiants, not only does the fact that they have an extended atmosphere complicate things, is the fact that they also have pulsations at the same time. So it's not really something that you can just study individually. So you can make a model with just the extended atmosphere or just pulsation. You have to track both of them. And so then tracking down what's causing what, and also they're eccentric. So I think it's going to make the problem much more difficult to address. And just as a sort of anti-publicity against me, I'm not going to specifically talk about this in the talk tomorrow. Feel free to talk about me whenever. Just the talk will be more supernova-ish connected. So, but yeah, feel free to talk to me about this whenever you want.
Thank you. Thanks very much. Any last burning comment someone wants to make? Oh, yeah.
I wanted to react about stellar winds. I heard many people using the Dutch scheme, for example. It's way outdated. You want to check recent literature. Also, if you check recent literature, sorry, don't use Bézer's mass loss rate for red supergiant because it's not correct. It's been demonstrated. It was computation. I mean, there was a mistake in the analysis. Check this 2024. No, 23, it's last year. But the question I had.
You should add these things to the slides. So do add some of these things, like don't, that's what we were kind of going for, like don't do this, do this, what's best practice.
My question was, nobody mentioned 1D versus 3D in those uncertainties.
We talked a lot about it.
It's not on the slide. So as an observer, I was wondering how wrong we are, or correct we are.
I mean, it sounds like from what Matteo says, everything is dealt with in some kind of prescription on each individual thing, and that might be okay if we understand the physics of those things, but they have really complex interplay between them, and I don't see how you can do that in 1D. Yeah, I mean, I don't know if we understand the physics, number one, but can you do even the interplay between them? If you need the 3D model, I'm a 3D person. I'm biased. I like it.
Before you can answer the question of can you put them together in one leaf?
Yes, and the way to understand the physics is.
We don't understand the physics, right? Because otherwise we would not run the simulation.
I don't know how much.